Okay, so in this lesson we're going to look at the three-dimensional delta function. First off, I just want to draw up here our position vector. Okay, and the position vector, which is r, extends from the origin 0, 0, 0 to some point given by x, y, z. Okay, so r is equal to x hat plus y hat plus z hat. Now for the three-dimensional delta function, we can write this down as delta r, which will be equal to delta x in terms of y and in terms of z. Now this three-dimensional delta function is going to be 0 everywhere except for at the origin, where we have x is equal to y is equal to z, which is equal to 0. At the origin, it blows up. Now what we can do is we can take the volume integral of this, and we will do the volume integral over all space. d tau. And this is going to be equal to the triple integral of each of these. And for each of these, our integral is from minus infinity to plus infinity. Okay, so we have delta x dx, dy, dz. Okay, so the integral of each of the delta functions with respect to x, y, and z is going to give us an answer of 1. Now, again, at the origin, it blows up, and everywhere else, the delta function is equal to 0. So we can extend this and generalize it. So we can shift the position, obviously, from the origin to some position A. So here we have the integral over all space, some function times our delta function, which will be given by r minus a d tau, so it's over all space. And essentially what this does is the integration will just pick out the value of the function which is located at the spike, which is going to be located at A. Okay? So this is very similar to the 1D case. So it takes the value of the function at the location of the spike. Now let's return to the problem that started all of this off. So initially we were looking at our vector function, which was given by 1 over r squared r hat. And what we expected was this to be strongly divergent. Whenever we took the divergence of this vector function, we found that it was equal to 0. However, we found that the surface integral, or the calculation of the flux, was equal to 4 pi. So now what does that mean? Well, essentially what we have is the divergence of 1 over r squared r hat. This is equal to 0 everywhere except for at the origin. Okay? So this tells us that what we have is a delta function. So this should be equal to 4 pi by the delta function of r. Okay? So this, the divergence of our vector is 0 everywhere except for at the origin. Now, of course, whenever we do the integral now of this, the volume of our vector v, what we're going to obtain is 4 pi, which is equal to our surface integral. Now, finally, we can write this out in terms of our separation vector, which is r minus r prime. And what we have whenever we write this out, more generally in terms of our position vector, we are going to have the divergence of 1 over r minus r prime to be squared, and the separation vector, the unit vector, is r minus r prime over r minus r prime. Okay, that's our separation vector, and this, our separation unit vector, is equal to 4 pi, and here we have our delta function in 3 dimensions, r minus prime. Now, one thing to note from this is that the source vector, so the r prime, is kept constant, and we are taking the derivative about the field vector, which is given by r.